I'm Andy Bell, and I'm going to be talking about, as you said, the age period cohort identification problem, which I think is actually probably one of the most important issues that has been addressed by some people, but is often quite misunderstood. And I'm going to be arguing in this talk that it really does matter quite a lot. So I'm arguing that differentiating between age period and cohort effects is impossible, first of all. So because they are collinear between them, it's impossible to tell one of them without understanding the others. But on top, as well as saying it's impossible, I'm also saying it's necessary. And so when modeling any of age period and cohort, if you're interested in age, you have to consider the other two, because implicitly they're going to be in your model as well. So you have to think about them, you have to think through the implications of them, otherwise you can end up making some really quite incorrect inference. So I'm going to quickly define what age period and cohort effects are. I'm going to talk about the age period cohort identification problem. I'm then going to talk about one solution to the age period cohort identification problem, which is the hierarchical age period cohort model, which was created by Yang and Land in 2006. And I'm arguing that this model this has been kind of billed, and it's been taken up quite a lot as a solution to the age period cohort identification problem. And I'm going to argue that it doesn't work, and that there are a number of problems with it, but that you can then overcome these by making certain strong assumptions, and I'm going to illustrate that with an example of mental well-being. So age period cohort effects. So I'm quickly going to kind of use this narrative, which comes from a paper by Suzuki, to kind of define what age period cohort effects are. So age effects are effects of aging, so effects as you go through the life course, you change. That's an effect of age, so I can't seem to shake this tired feeling. I guess I'm just getting old. It's an aging effect as you go through time. Then we have period effects, so that the period effect is something specific to a period of time, a year, or whatever period of time you're using. So it's something that affects everyone in that year. So for example, a business cycle, you have a period of time where perhaps business is down. Do you think it's stressed business is down this year? Something that's happening in that period of time. And then you have cohort effects, which are something to do with how people are, that's how a generation of people are different from a previous generation or a following generation. So here at the bottom, young people these days are quick to whine. We were not like that. The idea that an older generation has a different, something specific to them that's different from other generations. And so there's change that could happen over time across generations. So all those three definitions kind of make sense, and they're all potentially of substantive interest to researchers as to whether these effects are happening. The problem is that they're all exactly collinear, such that if you know the age of someone and you know the year of the measurement, you also know what year they were born in. You know their cohort. And because you know this, you have this exact collinearity, this confounding. And normally when we think about confounding in regression and things like that, we often are thinking about two variables that are kind of similar. But this is more than that. If you have two variables that are kind of similar, you can collect more data and find more out about them. In this case, you can't do that. They are mathematically or logically confounded, not just experimentally confounded. And so this presents a much more tricky problem that we need to deal with. And so, like I said, we can't hold age and cohort constant and vary period, which is what you do experimentally. If you wanted to run an experiment, you want to be keeping everything else constant and varying one variable. You can't do that with age period and cohort. And so this has led to some quite strong, but I think justified claims that there are no direct evidence for these kind of causal factors, and that attempts to separate them are one of the most bizarre instances in the history of social sciences, repeatedly attempts to do something that is logically impossible. So these are quite strong claims that have been made for quite a while in social science history. And yet people keep trying to trying to do something with age period and cohort. Just to be clear about this, what I'm saying is that if say you're interested in age and you have age in your regression model, you implicitly also have period and cohort. And so you need to think about what those two are doing to your results. Just to give you an idea, we have here three data generating processes. So three ways in which a health outcome is created. And so on the top one we have 3 equal age period and cohort effects. So there's an effect of aging, an effect of time passing, and an effect of generations replacing each other. The second one, we have 2 bigger effects of just age and cohort, and the third one, we just have a period effect. And if you do these data generating processes, these 3 processes are going to produce exactly the same outcome. The y variable will be exactly the same from each of these 3 equations, which obviously means that if you're trying to say which of these is the truth, how big is your age effect, you're really going to struggle to do that. You have a data set, each of these 3 possible outcomes fits your data equally well. So if you're interested in age, you could have an age effect of 1, an age effect of 2, an age effect of 0. You could also have negative age effects with the right combinations of periods and cohorts offsetting them, and they would all produce the same data set. So there's no way, given that data set, that you can tell which one is creating it. So what can people do about this? Well, you can't put all 3 in a regression model. The model won't run because you have exact collinearity. It's just like you couldn't put your height in inches and your height in centimeters into a model, you can't put all 3 into a model. One way to break this collinearity is to group one of age period cohorts. So often you see people grouping cohorts into 5-year groups, and this does solve the problem of collinearity, but it does it in an arbitrary way. Unless there's a reason to believe those groupings are accurate, and very rarely is there reason to believe the groupings are accurate, you will end up with arbitrary results that depend on the grouping you end up with. So the results you end up with, you might get one of these estimated, but there's no way of knowing whether it's the true one that you're estimating. So another solution, which is from a 2006 and then a series of other papers after that, a paper by Yang and Land, is to use a multi-level model. So I'm from the Center for Multi-Level Modeling, so I'm naturally inclined to these kinds of models. This is a cross-classified model, which means that, so we have multiple levels, so we have individuals at the lowest level, and then they're cross-classified into a period, so the year in which they're measured, and their cohort, so the year in which they're born. And this cross-classification is a way of creating a kind of model that, hopefully, as the authors want, is that it will solve this problem. So you have, in your model, you treat age as a fixed effect, so this is a quadratic polynomial. So age is treated as a curve, I suppose. And then you have cohorts and periods, which are treated as random effects. So they're treated as random fluctuations around any kind of age effect. And the idea is that by separating out these effects into one in the fixed part and these in the random part, you solve the problem. And that's what Yang and Land argue. They have these quite strong claims that the under-identification problem has been resolved, that it does not happen in this model. Contextual effect, someone in the way. The contextual approach helps to deal with, actually completely avoids the identification problem. So they believe that this model solves the problem. Unfortunately, it doesn't. So there's a paper there which you can look at, a simulation study we did which showed this, but I'm going to illustrate it with the example of obesity. So this is a paper by Reiter, Hauser, and Yang, and they ran their hierarchical age period cohort model and came up with results something like this. So they found a curve in the age effect. So as you age, your probability of obesity increases and then decreases into old age. They found pretty much no cohort effect, and they found a very strong period effect. So we simulated data that was slightly different. We simulated data that had a much larger age effect that continued through until very old age. We simulated a cohort effect there, and we simulated no period effect except for random fluctuations across years. And so we ran the hierarchical age period cohort model to this data, and the results that came out look very, very similar to Reiter et al.'s results. So that suggests quite clearly that if that's the case, it could be that this data process is what generated the Reiter et al. Data. So there's no reason to think that this is the truth as opposed to this. There's no reason to think it's the other way around, of course, as well. But what I'm going to argue is that, in fact, what you want to do is think about theory and make some assumptions based on that. So as a multi-level modeler, I don't want to throw this model away. I quite like it. It's quite intuitive. I like the way that it uses context and periods as a as contexts in which we kind of exist. And I like that you can use it as a multi-level model because that has a lot of extensions that you can use with it. And so what you need to do then is to think about which of age period cohort are most likely and make some kind of assumption about one or more of them. So often I would argue that one might want to constrain period effects to 0. So I would argue that often you would have you might have some random fluctuations in periods, but having a general trend through time is unlikely. And so you can do this quite easily by simply adding a cohort polynomial trend here to the model that we had before. So we have our age effect like before, have our cohort and period residuals as before, but we're now additionally adding a cohort effect, which implicitly constrains the period effect to be 0. And I'm going to illustrate this with an example of mental well-being. So there's been quite a lot of literature in the last 5 or 10 years looking at what the shape of the life course of mental well-being is. So how do we, as we get older, how does our mental well-being change? And the previous consensus is not quite a consensus, but the most kind of dominant viewpoint in this is that there's a kind of U-shape happening. So as you go through life until middle age, your well-being declines down to what you might think of as a midlife crisis. And then as you go into old age, your mental health improves as you get older. Now, when I came across this, that seemed kind of surprising to me because given issues that many of us will know about old age and loneliness and dementia and all sorts of other things like that. And so it seemed to me that quite likely that there might be something going on here about age period cohort issues that could be finding this result. And so as I said before, I'm constraining period effects to be 0. And I'm assuming that any change that happens through time happens as a result of cohort replacement rather than as a result of periods. And I've measured mental health with the BHPS GHQ score from 1991 to 2008. And I've done some other stuff which you can look up in the paper, but it's not actually that relevant to what I'm talking about now. And so this is the result that, this is kind of the data with the age and cohort effects combined. So you can kind of see, if you kind of squint a bit, that you can kind of convince yourself, if you kind of cut off this data here, that maybe there's a bit of a U-shape going on, that as you get to middle age, your health is at its worst, so high is bad health here. As you get to middle age, your health gets worse, and then it improves into old age, unless you get very old and then things start going wrong again. The problem is that this at the moment has age and cohort effects combined. So with this model, we can then take out the cohort effects, just look at the age effects, and this is what we find. There is now, well, perhaps a bit of a decline here for men, but nothing really that's significant. The general trend is a continuous worsening of mental health as you go through time. There's a bit of a slowdown in middle age, but there's certainly not the downward improvement that was found by in the previous literature. Blanchflower and Oswald is the classic paper for that. So this is suggesting that, in fact, what we were finding was not that as you get older, things improve, but actually what we were seeing was that older people were generally from earlier cohorts, and that was why they appeared to have a better health. It wasn't that they were old, it was that they were born earlier. In fact, it looks like, if we're assuming that period effects are 0, it looks like, in fact, mental well-being worsens through the life course. And we can also look at cohort effects, which can be of substantive interest as well. And so this is what we have here. So we have both our quadratic trend that we found generally, like this overall average trend, and we also have the stochastic variation from our cohort residual around that. So we can see that we have this general worsening of mental health over time as generations replace each other, particularly for women. And there's also a bit of stochastic variation there. If you want to try and kind of interpret this, you could perhaps point to people born during the 30s and during the 70s, during recessions. They seem to have better mental health. This is a slight overinterpretation of the data possibly, but perhaps worthy of further work. But there's something interesting going on in a general cohort trend of worsening health. So to conclude, my main conclusion methodologically is to be careful. There's the age period cohort. If you're interested in anything really that changes over time, you need to think carefully about the age period cohort effect, because it's likely that this is going to be affecting what you're doing. If you have age in your model, if you're interested in age, you also need to think about period and cohort, which of those two you think is most likely to have caused your effects, and model that based on that. Treat anyone that claims to have found a mechanical solution to the age period cohort with an appropriate degree of skepticism, because they seem to come along kind of every 10 years, a solution. They're never really a solution. There's always worth checking with simulations and things like that. And the assumptions that you make about age period cohort need to be based on theory if the theory exists, intuition if it doesn't. And that's because realistically in science you want things to be able to be challenged. You want to be able to have people coming and saying, well, actually your assumption that you made there is not really justified. I would say that in fact you want to make you want to be very clear about what you're assuming, which often these models which claim to solve the problem also make assumptions, but those assumptions aren't clear. And so it's important to be very clear about what your assumptions are. If you want more information about this, there's various papers here which you might be of interest. I think all these slides are now online, so you can have a look at that at your leisure. But there's various papers that look at this, do simulations, and then this is the substantive paper that looks at mental well-being. Thank you very much. That's everything.